In this video, I just want to do another example of a system of differential equations, and in this case, it's two competing species. So I didn't write all the assumptions out, but the idea is that you have maybe deer and elk in the same area, so they're both trying to eat the same stuff. And so you can see, and also we put in that logistic model, so both of them, there's a carrying capacity for both species individually, but also notice the interaction between the two species have a negative impact on both species growth. So of course this one has a bigger impact, so that probably means that potentially the Y is a bigger animal, so it needs to eat more. So being or maybe the X is the X animal needs to eat less, so or maybe it eats other things that the Y species doesn't eat or whatever. But for some reason, the interaction between the species has a bigger negative impact on the Y population than on the X population, but both have a negative impact. So that's and so we can take this and look at some a directional field. So I've got that here for you. I'm going to pull this up. Let me just actually pull that down. So there's the directional. You can see I typed the equation in there already. And this is a directional field. You can see that everything's kind of pointing down here except for right down here in the bottom. So I'm going to put in a couple of examples. So if I say click up here, let's say we start out with say 7 of one and that'd be about 2 of the other. Go right there. And then we'll do one down here like 4 of the X and 1 of the Y. And so you got some weird looking shapes going on here. And so notice they're all coming down to a flat line down there, kind of, or actually it looks like a sort of an asymptote. So, and notice on the inside we got the same thing going on. So there's something interesting happening along this space here between 3 and 2. So what we're going to go back, now we're going to go back here and look at what that is. So what we're going to do is look for some equilibrium points. So meaning that when is the change in X 0 and when is the change in Y 0. So we'll start off by just taking the change in X and say, let's distribute that 2x through, so that'd be 2x minus x squared minus xy. And we're going to set that equal to 0 and try to find out when that's equal to 0. So I could factor out an x, and that would leave me with 2 minus x minus y equal to 0. So definitely when x equals 0 is going to be one of my equilibrium points. And then 2 minus x minus y, that would be another one, okay? And then if we look at the y one, that's going to be 3y minus y squared minus 2xy. So that equals 0. And if we factor out a y, that'd be y times 3 minus y minus 2x. And so again, y equals 0 and 3 minus y minus 2x equals 0 would be the potential equilibrium points. Okay. So definitely if we take x equals 0 and pair it with a y equals 0, that's going to give me the point 0, 0. So that's a point that that is an equilibrium point. Likewise, if I take, so let's say that's x equals 0 and y equals 0. And then let's also take x equals 0 and 3 minus y minus 2x equals 0 and see what that produces. So if x equals 0, then this would be 3 minus y is equal to 0, because that would just be gone, which means 3 is equal to y. So that would produce the point 0, 3. And then likewise we could take, well, y equals 0. We could pair that with 2 minus x minus y equals 0. And that means if y is equal to 0, that would give me 2 minus x equals 0, which means 2 is equal to x. So that would give me the point 2, 0. And then finally, we would pair up 2 minus x minus y equals 0 with 3 minus y minus 2x equals 0. And for this one, we'd have to solve a system of equations. So let's multiply this one by -1. So that'd be -2 plus x plus y equals 0. And then just add that to 3 minus 2x minus y equals 0. If I add those two together, we get what? 1 minus x equals 0, which means x equals 1. And when x equals 1, that would mean y is equal to 1 also. So that would give us the point 1, 1. Okay? So we have these special points. Let's put them all together. 0, 0, 0, 3, 2, 0, and 1, 1. So now let's go back to our our drawing and see what's happening to those points. So you can see, 0, 0 will be right there, of course. 0, 3 is right up here. 2, 0 is right here, and then down here on the edge, and then 1, 1 is right there. So you can see this line that's kind of weird things are happening runs right along the line of equilibrium points. And as we talked about the other day, all the different initial points or initial conditions tend towards a equilibrium point, right? So all these guys are heading down towards the 0, 3 one, right? 0, 3. This guy's heading up to the 0, 3. This guy heads to the 1, 1. These guys are coming down to the 1, 1. These guys are coming into the 2, 0. So as we saw in when we were dealing with the phase lines in just a single differential equation, those equilibrium points generally the solutions go away from them like a source, or they came towards them like a sink, right? So we got the same idea going here. In this case, all the equilibrium points except for 0, 0 are going towards them. Notice the 0, 0 things are going away from it. In fact, let's look at that if we were to make this bigger. So we'll go to maximum, minimum, say -10. Of course, it doesn't really make sense in terms of population, but just so we can see what these graphs look like, you can see that things are going away from 0. You can even see how the arrows are going. Everything's going away from 0 and possibly coming back to those equilibrium points. Isn't that cool? I love these drawings. Now let's go inside. Yeah, there you go. So anyway, that's just another example of a differential equation and looking at the geometry of it. And this one's a little bit more complicated, so I wanted to show you this idea of finding equilibrium points, because the equilibrium points can tell us a lot about the geometry of the system of differential equations. So, all right.